Now let's look at some applications of exponential and logistic um, and logarithmic equations. Before we do that, let's look at a little bit of vocabulary, um, and we'll talk about how and why we're going to apply these terms as we go through the examples. But we're going to use the order of magnitude to compare any like quantities. Okay, we'll see that a little bit later. Okay, we're also going to look at the Richter scale model. Okay, the formula for that is R equals log of A over T plus B. Okay, all right, this formula measures the magnitude R of an earthquake, where A is the amplitude in micrometers of the vertical ground motion at the receiving station. T is the period of the seismic wave in seconds, and B is the dampening of the seismic wave as the distance from the epicenter increases. So these are values that we would be looking for in our word problem. But this is our model for a Richter scale. The pH scale model, pH is equal to negative log, okay, of this value. Okay, it says this is a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. All right, so we'll look at some applications involving that. We also have Newton's law of cooling. The formula for this is capital T of lower t. Okay, we'll talk about what those values mean. Equals T sub m plus T sub 0 minus T sub m e to the negative kt, lowercase t that is. Okay, so what are all of these values? It says the temperature, T. So capital T represents our temperature of an object at time t. Okay, so that's what this is. Temperature of an object at time t, where T sub m equals the temperature of the surrounding medium. Okay, so that's what we got right here, T sub m. All right, and T sub 0 is the initial temperature of the object. Okay, all right, this T um, in our exponent, again, is our time. Okay, so what's really important is that you understand what these different variables represent. Um, I won't be asking you to memorize these formulas, but you will need to know what the different values mean so that when you see the word problem, you'll know what to plug in where. All right, let's do a little exploration with the orders of magnitude. Okay, it says using a calculator, compute log of 3 times 10 and log of 3 times 10 squared and so forth. Okay, so let's see if we can do that on our calculator. All right, we're going to do log of 3 times 10. We get 1.477. Okay, if we do log of 3 times 10 squared, Okay, we get 2.477. And if we do log of 3 times 10 cubed, we get 3.477. Okay, so we see a pattern there. Okay, so it says, what is the pattern in the integer parts of these numbers? And so if we look on the calculator, we see that the integer part is going from 1 to 2 to 3, right? Okay, we got the 1 there, 2 here, 3. Okay, so that's that part. So for question 2, it's 1, 2, 3. And if we were to go all the way up to 10, I think we would see that the final value is going to be 10. Then it asks, what is the pattern of their decimal part? So we can see that for each decimal part, we've got this 0.477 number. Okay. And so question 4 says, how many orders of magnitude greater is 3 times 10 to the 10 than 3 times 10? Okay, and the answer to that is just the difference in the exponents. Okay, what we're going to look at is just 10 minus 1, all right, because we're just taking that from the exponents. Of course, we understand that there's an exponent of 1 there, and then we can see the exponent of 10. So we got 10 minus 1, or 9. How many orders of magnitude greater? So basically, we're talking about the differences in the powers between these two values. To go from 3 times 10 to the 10 to 3 times 10 to the first, that's going to be 9 orders of magnitude greater. All right, that's what that means. So in the next example, we're trying to compare earthquake intensities. How many times more severe was the 2001 earthquake in India, which had a Richter scale value of R1 equals 7.9, than the 1999 earthquake in Athens, Greece, which had a Richter scale rating of 5.9? Okay, so to solve this, we're just going to look at the difference between R1 and R2. Okay, remember we saw our formula for uh, Richter scale. So for um, R1, we're going to have log of A1 over T plus B. Okay, minus log of A2 over T plus B. Okay, we'll assume that the T and B values for um, the earthquakes were the same. All right, so T was the period of the seismic wave in seconds, and B is the dampening of the seismic wave. But we'll assume that those values were the same for each of the earthquakes. Okay, but for now, this is our formula. Let's see, for R1. Okay, and then this is our formula for R2. Okay, so just wrote the formulas down. The only thing that's different between them is the A1 and the A2. Okay, so let's see if we can simplify this sum. Notice that I have plus B here. Okay, and then when I distribute my minus sign, this is going to be minus B. Let me write all of that out. We've got log of A1 over T plus B minus log of A2 over T. And when I distribute the minus, that's going to be minus B. So the B values cancel out. Okay? And so from here, we can try to figure it out. Okay? We've got, this is R1 minus R2, but they gave us values for these. R1 was 7.9, and R2 is 5.9. Okay, and this is going to be equal to log of A1 over T minus log of A2 over T. Well, here on the right side, I think I can apply my log properties for division or a quotient, right? I can rewrite this as log of A1 over T over A2 over T. Okay, we're taking the log of that quotient. And if I were to reduce this, let me do an aside here, A1 over T divided by A2 over T equals A1 over T times T over A2, right? When I'm dividing by a fraction, it's the same thing as multiplying by the reciprocal of the denominator. The T's cancel, and so that leaves us with A1 over A2. All right, so this is equal to log of A1 over A2. All right, and in fact, for our purposes, we can reduce this to R1 minus R2 is equal to log of A1 over A2. Okay, all right, we know the difference between R1 and R2 is 2. And so we want to solve this, figure out what the ratio of A1 to A2 is, and this is where we use our definition for what a log means. Okay, this is log base 10, and so this says if I take 10 and raise it to 2, that's going to equal A1 over A2. All right, and so what we can say is that India, the earthquake in India was 100 times greater than the earthquake in Greece. All right, so just as a recap, a lot of this was just kind of reducing the equation to what we needed. Um, but remember the question asked how many times more severe was one earthquake than the other, okay? And so we're looking at R1 minus R2, and we were able to reduce our expression for R1 minus R2 to this equation. Okay, so, in future, if you're asked this question, instead of having to go through all of this work to do the reduction, if you remember or have access to this, you could just use this equation. Okay, then we plugged in our values for R1 and R2. We found that we had a difference of 2, And we were able to use our definition of the log to rewrite this as an exponential expression. If we have 2 is equal to log of a1 over a2, then that's the same thing as saying 10 squared equals a1 over a2. And so that's how we know that the earthquake in India was 100 times, because 10 squared is 100. It's 100 times greater than the quake in Greece. Okay, in this example, we are looking at trying to determine the hydrogen ion concentrations of balsamic vinegar and baking soda. Okay, so we'll do it for vinegar first. And so we saw that we had a formula earlier that the pH was equal to negative log of the hydrogen ion concentration. Okay, so we're looking at, for vinegar, a pH of 2.4, okay, is equal to negative log of the concentration. Okay, so I can rewrite this. First of all, I'm going to multiply both sides by -1, so I get negative 2.4 equals log of hydrogen ion concentration. And we use our definition to rewrite this as an exponential equation. We've got a base of 10. So this says, what do I raise 10 to get this ion concentration? The answer is -2.4. I can rewrite this as 10 to the -2.4 is equal to the hydrogen ion concentration. So it is 10 to the -2.4. On our calculator, we can do uh, 10 to the -2.4, and we get 0.00398. Or if we wanted to write this in scientific notation, this is going to be 3.98 times 10 to the -3, okay? Because to get back to this number from this number, we need to take our decimal point 3 places to the right or to the left. And so that's going to be 10 to the -3. So that would be our answer, 3.98 times 10 to the -3. Okay, we can do the same thing for baking soda. Okay, so we've got the same formula. The pH is equal to negative log of the hydrogen ion concentration. And so they tell us that the pH for baking soda is 8.4. So I can multiply both sides by negative. I get negative 8.4 equals log of the hydrogen ion concentration. And so from here, I can rewrite this in exponential form by saying 10 to the negative 8.4 equals that level or measure for the hydrogen ion concentration. Okay, and so if we do that on the calculator, we get 3.981 times 10 to the negative 9. All right, they've already got that one in scientific notation for us. Okay, so part B of this question says, how many times greater is the hydrogen ion concentration of the vinegar than the baking soda? Okay, so to answer that in part B, we're just going to look at the ratio of what we found for vinegar over what we found for the baking soda. All right, so for vinegar, we found earlier that the hydrogen concentration was 10 to the negative 2.4. And for baking soda, we found that it is 10 to the negative 8.4. All right, so when we simplify this, we get 10 to the negative 2.4 minus negative 8.4. And so when we simplify that, it's 10 to the 6th. So we can say that um, the hydrogen ion concentration of vinegar is 10 to the 6 times greater than that for baking soda. Or in part C, if we answer by how many orders of magnitude do the concentrations differ, the answer would be 6. Okay, here's our last application, and this one has to do with temperatures. Okay, it says a batch of brownies are taken out of the oven, out of a 375-degree oven, and um, cools to 150 degrees after 20 minutes in a room at 70 degrees. Use Newton's law of cooling to determine how long it will take the brownies to cool to 90 degrees Fahrenheit. Okay, so the first thing we're going to do is write out our formula for this law, okay, which is the temperature at a particular time is equal to the temperature of the medium or the surrounding medium, the area, plus our initial temperature minus the temperature of the surrounding medium times E to the negative KT. Okay, where T, that lowercase t is time. All right, so let's identify some of these things in our scenario here. The 375 degrees, that's our initial temperature. Okay, and the 70 degrees, that's the temperature of the surrounding area or surrounding medium. All right, okay. Um, Then we're given a particular point in this situation. We know after 20 minutes, the brownies cool to 150 degrees. All right, so this is a point, and we can use that point to help us figure out what the value of K is. Okay, we've done activities like this before, but first we need to figure out what that K value is, and then once we have a better model, we can move on to using that model to answer some question. Okay, but for now, this is the information that we have. So let's see if we can plug this in. Okay, our basic model is now T of T equals the temperature of the surrounding medium plus our initial temperature minus that temperature of the surrounding medium, e to the negative kt. Okay, that's our basic formula. We're trying to figure out what k is, and we have a particular point when the time is 20 minutes, then the temperature was 150 degrees. So I'm going to plug that in. Okay, for T of T, I can put in 150 is equal to 70 degrees plus the difference here is 305 degrees, e to the negative k, and t in this case is 20 minutes. Okay, now in this expression or this equation, I only have one unknown value, that's k. So we need to solve for k. All right, so I'm going to isolate the term that involves k by subtracting 70 from both sides. And I get 80 is equal to 305 times e to the negative 20k. All right, then we can divide both sides by 305. So I've got 80 over 305 equals e to the negative 20k. All right, we can take the natural log of both sides. And the reason I'm doing that is because I'm trying to get to that k, which is in my exponent. All right, so, and when I take natural log of e to the negative 20k, we know that e and natural log cancel each other out because they are inverses of one another. So I've got negative 20k is equal to natural log of 80 over 305, or k equals natural log of 80 over 305 divided by 20. Okay, on my calculator, I'm going to do natural log of 80 over 305. And then we're going to divide that by 20. And I get k is equal to negative 0.066914. Okay, I'm going to store that in my calculator by hitting the store key and alpha, and you can use any variable, but variable k is on the left parenthesis. Enter. Okay, now we've got it stored. with all of the bits and pieces. Okay? All right, so now we can make it an even better model. Okay, we had that T of T was equal to 70 degrees plus 305 degrees e to the negative kt, but now I can put a value in for k. Okay, so my equation is going to be T of T is equal to 70 plus 305 e to the negative, right, 0.0669 t. Okay, we don't have to write out all the decimal places because we stored them in our calculator, so we can round when we're writing it out. All right, so now that I have this model, I can answer the second question, which is use Newton's law of cooling to determine how long it will take the brownies to cool to 90 degrees. Okay. So we want to figure out, it says use this law to determine how long it will take the brownies to cool to 90 degrees Fahrenheit. So we want the end temperature, which is represented by T of T, to be 90. And notice that the question is how long. So that means we're going to be trying to solve for T. And T is right here. So how long does it take for the temperature to get to 90 degrees? So I'm going to plug in 90 equals 70 plus 305 e to the negative 0.0669 t. Okay, we subtract 70 from both sides, so that's going to give me 20 equals 305 e to the negative 0.0669 t. And I can divide both sides by 305. So 20 over 305 equals e to the negative 0.0669 t. And now to get to that t, I can take the natural log of both sides. Okay, of course, natural log and e cancel out. And so we've got natural log of 20 over 305 equals negative 0.0669 t. Remember this negative 0.0669 number is our k value, which we stored in the calculator. So I'm going to say t equals natural log of 20 over 305 divided by negative 0.0669. I'm going to put dot, 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 just to remind me that I've got all of the bits and pieces of that number stored in my calculator. Okay, so when I go to the calculator, we're going to look at natural log of 20 divided by 305. Okay, and that's going to be divided by the k value, so alpha k. Okay, and we get 40.7 minutes. T equals 40.7 minutes. It'll take about 41 minutes for the brownies to cool to 90 degrees.